metric on it. That's why I said in the previous class that geometry cares about distance, topology doesn't. So that's why your metric spaces are, some special case of a topological space. So these are some examples of, some topological spaces and stuff. And then I'm going to go to another definition. This is another definition. And this definition is for the metric spaces. Or so to say, we are talking about metric topology. This is the point where, you start to deal with the metric. You define some distance and stuff. So first, let's define what is a metric. Definition. Metric. A metric okay, let's make this a little bit bigger. R is a function that satisfies the following conditions. If I remember correctly, this should be a product topology, this x cross x. But we are not going to discuss product topologies, basis, subspace topologies. That's another thing. So we don't need it for this course, okay? If you are interested, I suggest you audit the course on topology. I think Turjo is taking it. It will be a good refresher for you people if you want to take that. Okay, so that satisfies the following requirements. And there are tons of proofs and stuff to do all these things. You need to prove tons of things, so I really don't want to go there. So this metric thing is defined by this D. So D of xy is equals to D of yx is called a symmetric property, or so to say, the metric has to be symmetric. The second one is that it is positive definite. Positive semi-definite. Yeah, this is called positive semi-definite. And the last one is the triangle inequality that you see in your high school. So how do we interpret this? Well, we interpret this as the following. If you are thinking from a physicist's point of view, then this D is nothing but a distance. So think of this D is like this. So this is a physicist's point of view. Let's say this is point X, this is point Y. Then this is our D of X comma Y. So the distance from X to Y and Y to X, they're the same thing. So that's where this symmetric term comes in. It has to be positive definite. Well, why it's greater or equal than 0? Well, you can think that, distances are never negative unless you are dealing with some Lorentzian manifold and stuff like that, or Minkowski space-time stuff like that. But let's not consider that right now. It's just a choice of metric that we do. For now, let's confine ourselves, in some r to the power n. If you consider things like that, the distance is never negative. So that's why it's greater than 0, and it's 0 only when y is equals to x. So you are, dragging this y point to the point x. And this is the triangle inequality, right? So this is x, let's say this is y, and this is z. So this d of xy denotes this line, x to y, and this d of yz denotes a line from y to z, and this d of xz denotes a line from x to z, right? And this is just a triangle inequality. The sum of the arms of some of the two arms of a triangle is greater than the other one. So that's a physicist point of view. And a mathematician would define a metric like this. They won't call it a distance. Okay, so any questions so far?
No.
Okay. So there is a comment for any. So this is a comment. For any 3 points, let's say x, y, z belongs to the set X, if X is given a metric T, then X is made into a topological space. X is made into a topological space whose open sets are given by some open disks. Open disks. Oh, it's not the. It should be DISC disks, which are given by this relation over here. And they are all possible unions. And this type of topology is called a metric topology. This type of topology is called a metric topology. So what does this thing mean? What are these open sets? Let's try to think of them in terms of a physicist's point of view. So this condition is telling you that the distance between some point x and y is less than some very small parameter epsilon. So these disks are actually something like this, and they're called open disks. Why? Because they don't have a boundary. So you can think of this, if you consider this as a circle, a circle or a ball type of figure, then you can safely assume that the radius of that ball or the disk is less than some epsilon, where epsilon is very, very, very small. Even though the figure I draw is pretty big, this epsilon in reality is very small. So if you're familiar with the definition of a neighborhood, let's say this is a point on a real line, and sometimes we talk about some epsilon neighborhood in your complex variables, or in your calculus courses. This f of x minus y naught is the modulus of this thing. I think everyone saw this, right? Some epsilon. This is like a neighborhood. So this neighborhood is very, very, very small. So you can think of it like that. And you have this open disks, a collection of open disks, and they're the thing that lets you define your topology, or so to say the metric topology. They are your open sets for this topology. In fact, if I remember correctly, these are your bases. For a topology, you can go on and define some basis of topology as well, but we're not discussing that here. So any questions so far? Is it confusing?
Basis in the sense of like a vector basis in that sense?
No. They're entirely different.
Oh, I see.
The topological bases are entirely different. In fact, instead of those three conditions that you saw earlier, Like you have a set and you have a collection of open sets, and you have to do what? You have to satisfy the three requirements, right, to make it a topological space. But you can, what you can do is that you can construct some basis for a topology, and from those three requirements you can draw, extract out some requirements in terms of a basis as well. And no, it's not analogous to the basis we saw in your linear algebra course. No.
I see. All right.
Okay. Okay. Anyone? Anything else?
Sir, can you summarize the metric topology thing?
Yeah, this is the summary, right? This is the definition. It's just a definition right now.
Oh, I understood metric, but not metric topology. How does the topology come in?
You have some metric. You have a topological space. You define a metric, you get a metric topology. Or in a mathematical sense, you have some space. You define a metric like this, a metric D from, x with the Cartesian product with another x, two sets. You make their Cartesian product. So you get what? One of the sets will carry some terms like 1, 2, 3, 4, 5, 6, 7, 8, 9, da 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 da. And you make a Cartesian product with the other set. So now your new set, let's say x cross s, is given by some s. They will carry two items, right? X comma y. In general, we can write them like that, where x and y both belongs to capital X. So from there you define a metric. And how do you define a metric? Your metric should satisfy these three conditions. Okay. And on that x cross x, the resulting set, let's not call it space right now. On that resulting set, if you can have your open sets, which is given by this definition, some balls or some open disks, then that metric along with these open sets and their arbitrary unions will define your metric topology. Okay.
Does the ball has to be circular or any shape would do?
When you talk about balls, yeah, I mean, there is no, what do you mean by a ball? You are saying that your distance, this d of xy, is less than some epsilon, right?
Yes.
So any neighborhood you draw, don't they have to be the same? Do you get my point? Like what
Yes.
do you do in your ordinary calculus? In ordinary calculus, when you try to define your limits or continuity, you say that, oh, for some epsilon, maybe if I can find some delta, right? And what is epsilon there? You take a point on the real line, or so to say your x-axis, and you try to draw what? A neighborhood by x minus epsilon and x plus epsilon, right? So think of it like that. This is x, this is your x plus epsilon, this is x minus epsilon. And what's the distance from these two things? They're the same thing. This is epsilon, right?
Yeah, yes.
I guess what Farhan is trying to get at is that we're exploiting some sort of spherical symmetry here. But
No,
like
no,
what
no, no. I mean, these are abstract spaces. How can you even, put
I
some
see.
geometrical figure there?
All right.
They're, I mean, mathematicians just call it a ball. They don't even, as far as I know, they won't comment anything about uh, some spherical symmetry because it's a set. How can you attach a sphere inside a set? I mean, maybe you can do that. I don't know.
So how does the set have a condition like d of xy less than epsilon? How
That's
does
the
this condition?
definition. You cannot prove it. That's a definition. Can you prove any axiom? Can you
No.
prove 1 plus 1 equals to 2 for real numbers? No. That's how we define things. If you challenge definitions, then yeah, all the things are gonna, go to the drain. Okay. You can do that, but I don't think you will find a satisfactory answer.
Is the Cartesian plane metric space, metric topology?
Well, define something and try to prove it. I haven't proved it, so I don't know. But you do define, when you talk about distances, you do define a metric, right? And if you're talking about the two-dimensional Cartesian plane, take any 2 points on the Cartesian plane, right? And you can easily see that you can define a metric because these three conditions will get satisfied easily.
Yes.
So now the next thing is, can you define some open sets like this? You can, right? Can you? What do you think? You can always take some distance, right? This d of xy, which is less than some small epsilon in your two-dimensional Cartesian space. So you have open sets like this as well. So that should give you a metric topology.
Okay, got it.
Okay, so let's move on. Yeah, we have a lot of things to cover. So again, if you are interested in rigorous mathematical proofs, consult Mancres. The book is called Topology. If you care about the rigor, go to this book, Topology, our first course. Big book. It has a lot of proofs and exercises. So this is for people who care about the rigor. If you don't care about the rigor that much, well, you can stick to Nakahara. Or you can consult Crossley's book as well. So if you want to go for proofs, go for this book, Mancres. It's a very good book. Okay, so yeah,